Hello everyone, so welcome to lecture 28. Just to recap, in the previous lectures we were looking at phase diagrams. We were trying to derive various different types of phase diagrams. We have looked at the isomorphous one, we have looked at the one where alpha is a regular solution, liquid is an ideal solution, and that gives rise to congruent melting sort of phenomena that gives rise to spinodal decomposition, right. So, which also you can use for material growth, right. So, all these ideas that gives rise to eutectic phase diagrams. We have seen the example of VLS growth that can be explained and designed through this eutectic phase diagrams, and VLS is to grow single crystalline nanowires. And then we moved on to looking at what are called needle compounds. So compounds where the solubility of one of the species is very small, right. So, this is mostly a pure species, right. So pure compounds essentially, and in that phase, and that phase cannot take more of the other species. Species 2 cannot be put in more into ice, let us say. And using this example, we said in cold countries how so ice can convert, or when it snows, right. So you put the salt or antifreeze on the roads, and that helps it melt at temperatures less than the ice melting temperature, which is 0 degrees Celsius, right. So when the outside temperature is less than 0 degrees Celsius, still my ice melts because I am making it a bit impure, and this is, so we explained it through the formulation of a needle phase diagram. And the other example we gave is trying to estimate the number of thermodynamic vacancies in any material, right. So these are the various case studies that we did so far, and we'll start from there. And if you remember, in the previous class I gave you an assignment. I said, okay, so if we count based on the Arrhenius equation that we derived, if we count the number of vacancies per centimeter cube, if we derive the number of vacancies per atom, I have about 10 power minus 5 vacancies per 1 atom, right. Now I want to make this, so how many vacancies per centimeter cube? This is what I asked you to calculate, and maybe some of you may have done it. So I am going to roughly assume that the size of a unit cell, okay, these are the rough sizes, right. So most materials have sizes of the order of 5 angstroms, right. So 5 angstrom by 5 angstrom by 5 angstrom, and in 1 centimeter cube, which is 10 power 8 angstroms, sorry, 10 power 10 angstroms is okay, so, or 10 power 7 nanometers. So 10 power 7 times 10 power 7 times 10 power 7 nanometer cube, that is 1 centimeter cube. So this is the total number of atoms in 1 centimeter cube, right, divided by 0.5 times 0.5 times 0.5, right. So 5 angstroms is about 0.5 nanometers, right. And so that is just going to be 555, there will be 888 here. So that is, and this is also nanometer cube, right. So that is 10 power 24 divided by 125, that is equal to about 10 power 22 roughly, right. So 10 power 24 by 100, okay. So I have about 10 power 22 atoms in 1 centimeter cube, okay. So this is you can compare it with what the Avogadro number is. I am not going to, so this is a solid, so you do not need to have Avogadro number of atoms in 22.4 liters, but compare these numbers with how many molecules does a gas have, right. So at STP, okay, but this is a solid, so we made this calculation based on the assumption that this is a solid, okay. Now 10 power 22, for every 1 atom I have 10 power minus 5 vacancies. So 10 power 22 atoms, I have 10 power 22 atoms times 10 power minus 5, that is 10 power 17 vacancies per centimeter cube, right. So this is the vacancy concentration. At room temperature is 10 power 17 vacancies per centimeter cube. Okay. So, I can use just the Arrhenius formulation to calculate the number of thermodynamic vacancies in any system. Okay. All right. So, with that let us actually look at some of these needle compounds, right. So, phase diagrams of needle compounds. Now, what I said essentially so far is x2 equal to a phase with predominantly x2 equal to 1 or x2 equal to 0, right. So, these are what we said so far were needle compounds, right. So, essentially my G can be G of beta is either here, right. So, this is 1 and this is 2, or G of beta is here, I mean let us call this alpha, right. So, these are essentially pure, almost pure 2, beta is almost pure 2. Beta does not like taking more of 1 as an impurity. Here alpha is almost pure 1. Alpha does not like taking more of 2 atoms in it. If it takes more of 2 atoms, it will start segregating. Okay. Now, why should a needle compound only exist at either x2 equal to 0 or x2 equal to 1, right. So, why not, so can I find a phase diagram. So, this is temperature versus x2, where so this is some phase, this is some phase, this is some phase, but in the middle, right. So, I have sort of what is called a needle compound, right. So, this is at x2 equal to 40% or x2 equal to 70% or x2 equal to whatever, right. Such kind of compounds also exist. So, essentially only at x2 equal to 40% this phase is stable. This whatever this I am going to call this the gamma phase, I am going to call this the delta phase, right. So, delta phase can exist, or pure delta phase can exist only at x2 equal to some 70%. Okay. And if x2 is 73%, then I will have somewhere here I will have a combination of this beta phase plus delta phase, right. So, okay, something like that, let us say. So, I will have a combination of at x2 equal to 73%, I have a combination of delta phase plus beta phase, right. So, we can actually I can actually show you some phase diagrams that have such kind of what are called needle compounds or line compounds, because they exist across a line, right. So, that is why we call needle compounds also as line compounds. Okay. So, here is a phase diagram of a material GT. So, on one side is germanium telluride, on the other side is sp2te3. Okay. Now, this solid solution is going to give you what is called GETE and sp2te3, and the solid solution of this is called GST, and GST is, again I have discussed this earlier, it is a phase change material for phase change memory, right. Essentially I can switch GST based compounds from 0 to 1 by switching them from amorphous to crystal and crystal back to amorphous phases. Okay. So, I think we have had this discussion earlier, so I will not go into the details of the crystal amorphous phase transition, but this is a very well known memory, so it can be used as computer memory, it can be used as optical memory on CDs and DVDs and so on and so forth, right. So, if you watched any movies using CDs and DVDs, and I think we took the example of Basha, Rajnikant's Basha, right. So, when at least 10-15 years ago Netflix used to supply DVDs, right. So, with movies encrypted on that, and the active material where all your entire movie is encrypted is actually a phase change material. Okay. And it will have composition which is somewhere in this phase diagram, right. So, GETE sp2te3. Okay. Now, so it's a technologically important phase diagram, right. Now, you can see that okay, so there is some alpha phase of GET here. So, alpha phase here, let us say this is the beta phase, okay. But between alpha and this is the liquid phase, right. So, this is alpha plus liquid, this is beta plus liquid and so on, but at various compositions, right. So, this is GE2 and GeTe2 and Sb2Te3, right. This is GeTe Sb2Te3 1:1, and so this is the 1:2 composition, which is also there is a small area, but it is more or less like a line compound, right. So, all these things, this one, these are all what are called line compounds. Okay. So, right. So, what are the line compounds we have in the GeTe Sb2Te3 phase diagram? We have a line compound which is GeTe 2 Sb2Te3, that actually if I write it completely, it is Ge2 Sb2Te5, and this is what is called GST225. This is the most famous composition, most famous phase change memory composition. Okay. And if I actually look at the structure of this, right. So, this is a van der Waals bonded structure. Okay. It is a chalcogenide. Chalcogenide means I have not oxygen, but elements of group 6 which are not oxygen, right. So, selenium, tellurium and so on. Okay. And if I look at the structure, Te, I have another Te, I have a Ge and Ge. So, this is 2 GETs, right. So, GET2, right, and then I have Ge will be bonded to another Te, okay, and there is an Sb, there is a Te and there is another Sb. Okay. So, I have an Sb2Te3 unit here and I have a GET, right. What about the next layer? So, I have these 9 layers 1, 2, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, right, 3, 4, 5, 6, 7, 8, 9. This starts with tellurium, ends with tellurium. So, here tellurium is an anion, right, germanium is a cation. So, I have a nice cation anion bonding, right. So, this is more or less covalent bonding with some ionicity. Okay. Actually, it's so nowadays people are calling it what is called metavalent bonding, but anyway, so let us not go into details of that. And this is the tellurium, this is the tellurium. The next set of layers start with tellurium, right. So, and then I have again these 9 layers, they repeat, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, it ends with tellurium. So, and then again it starts with tellurium and ends with tellurium and so on and so forth. So, these are the non-nipple layers, what are called the 9 non-nipple layers, right, that exist as a so on the top of each other, right. Now, here I have a very weak bond, tellurium bond is weak, and that is the van der Waals bond, right. So, as a result I can just peel them off using a scotch tape. Okay. So, this is a van der Waals material, okay, and as you can see, right. So, there is a particular way in which germanium telluride and Sb2Te3 are ordered, these are ordered, right. So, I have this is germanium telluride, this is I'll write germanium telluride in red, this is GT, this is GT, this is, and then in green, or I am already using blue, in green is ST. Okay. So, I have GT, ST, GT ordering, right, in this direction, right. So, in that direction is the C axis or 0, 0, 0, 1 direction, okay, and that gives rise to an ordered compound, ordered phase rather, okay, which is only pure at, which only exists rather at 2:1 GT to ST ratio, GT is to ST. Okay. So, any other ratios, well, I will have some segregation that is happening, right. So, if germanium telluride is not 2:1, it is some 2.2 plus delta, and Sb2Te3 is still 1, right. So, I will have this forming Ge2Sb2Te5, right. So, that is my ordered or needle compound phase plus delta times GET, right. So, it forms a phase mixture. So, one has to be very careful, because if I do not control the composition well enough, then I will be getting phase mixtures, and then my phase change material is no longer good for phase change purposes, right. So, same thing with the other compositions, right. So, the other needle compound you have, if I go back to the presentation, right. So, there is one at 1,1, right. So, this is what is called maybe I will just. So, this is what is called Sb2Te4. Okay. So, 1,2,4, this compound is called 1,2,4, this compound is called 2,2,5, and so on. Okay. All right. In fact, you can actually see, I think this is the structure. So, you can see the van der Waals bonds here, right. This is the structure, I believe, of 1,2,4 or 1, 2, 3, 4, 5, 6, 7. All right. So, I am not exactly sure what this is of, but we can sort of so back count it. So, 1, 2, 4 should have, this is 2 plus 2 plus 5 is 9. So, this is 1 plus 2, 3 plus 4, 7 layers, right. So, here is a 7 layer structure, and sorry, from here to here there could be some defects here. So, this looks like a GST124. Okay. So, and then I can actually count, let us say this is tellurium, this is again it should end in a tellurium, right, and so on, right. So, or maybe I will have to check about this, right. So, I will come back on what exactly this image is, but in general whatever I said, right. So, you have these nonupal layers or quintuple layers or 7-pal layers and so on and so forth, and you can see that there are these van der Waals bonds that exist in this electron microscope image. Okay. All right. So, so yeah, that is so that is the nature of what are called needle compounds, or needle compounds do not need to exactly exist at x2 equal to 1 or x2 equal to 0, but rather they can exist at other x2s, and so a slight change in composition, right, so is going to precipitate out some other phases, right. So, so it is not just 1 to 4, if the composition is somewhere here, I will also I will precipitate 1 to 4, but I will also precipitate out this phase, whatever this phase is. Okay. So, I can use the lever rule and say what phases are precipitated, but all these things, right, so are essentially what are called needle compounds. All right. So, with that, let us sort of end the discussion on phase diagrams. Okay, and begin our discussion on what is called reaction thermodynamics, right. So, like I said, ideally any thermodynamic process, I can see it as either a phase transition or some kind of a chemical reaction, right. So, phase transition we have seen, phase and then we have seen how to construct the phase diagrams and then look at these phase transitions. So, we will now go to the next thing where so I want to make something like barium titanate. I understand the various phases of barium titanate, which is okay, right. So, I understand what happens if barium titanate is mixed with some lead titanate, right. It is a binary compound, I understand the various phases that can come up, but how do I initially itself chemically get this barium titanate. How can I make this compound barium titanate, right? I have to do a chemical reaction for that, and that chemical reaction should be spontaneous, right? And like that, so in my growth process I will have to deal with many chemical reactions, and I will have to make them spontaneous. Even if they are not spontaneous at room temperature, I will have to change my temperature, pressure and conditions such that these reactions become spontaneous, right? So for example, just the example of barium titanate, I want to go to that temperature where barium carbonate and titanium oxide react to give rise to barium titanate, right, and then give off carbon dioxide. Carbon dioxide can just go away. Alright, so I want to actually understand reactions, right. So and then this is probably you did this in your high school chemistry, but so we will do it more formally now, and that brings us to the idea of what is called reaction thermodynamics. Okay. So in the next 2 classes or something, we will try to look at reaction thermodynamics, which is the last topic in this thermodynamics. Okay. So and then we will move on to surfaces, strains and elasticity and so on and so forth. Okay. Now, so let us formalize this, right. So I have any chemical reaction, and any chemical reaction can be written as 4A1 plus 3A2, some chemical reaction, right. So gives rise to 2A3 plus 6A4. This is one reaction, right. In general, I am going to write it as nu 1 A1 plus nu 2 A2 gives so nu 3 A3 plus nu 4 A4, right. So this is a generic reaction with 4 so 2 reactants and 2 products. So these are called the reactants and these are called the products. Okay. And just to put it more elegantly and mathematically, I am just going to write this as sigma nu I A I equal to 0, right. So here this is an equation or a chemical reaction, right. So and that means that my products minus reactants, right. So nu 3 A3 minus nu 1 A1 minus nu 2 A2, right. So that is equal to 0. This is how I am just going to mathematically write it, because then I can put in free energies and other things for these AIs, right. So and then it will become a legitimate mathematical equation, right. So I have just transformed this reaction into a mathematical equation. This means nothing at the current stage, but once I say AI is actually free energy of A1, right. So when it is undergoing this reaction at this temperature, at this pressure, then this becomes a mathematically relevant equation, right. So I am just going to write it like this. Okay. All right. So now when the reaction is progressing, right. So I am going to define what is called a progress variable of a reaction. Lambda. Okay, which means so let us say the reaction has progressed forward, right. So nu 1 A1 plus nu 2 A2 gives rise to nu 3 A3 plus nu 4 A4. So what do I mean by saying the reaction has progressed forward by progress variable lambda, defined by progress variable lambda? That means so I have n1 atoms of A1, n2 atoms of A2 have reacted to give dn3 atoms of A3 and dn4 atoms of A4. Okay. So I mean this is straightforward to understand, and as a result so I am going to say that okay, so the progress variable can now be defined like this, right. So I have a nu 1, right. So nu 1 times d lambda equal to dn1, right. So this is because the reaction itself has progressed by d lambda, right, which means nu 1 times d lambda equal to dn1, nu 2 times d lambda equal to dn2, nu 3 times d lambda equal to dn3, and nu4 times d lambda equal to dn4, right. So, the lambda is now more important, and so how are n1, n2, n3, n4 related? They are related through these coefficients to lambda, right. So, nu1, nu2, nu3, nu4 times d lambda equal to dn1, nu2 times d lambda equal to dn2, and so on and so forth, right. So, this becomes easy to just see, okay. So, you can think about this, and this turns out to be correct. So, then I can write d lambda is just dni divided by nu I, right. So, how much did the species I lose or gain, right, when I put it in the form of sigma nu I a I equal to 0, where this is products minus reactants, right. So, so how much did I gain in the species I, and what is its P coefficient, right, that gives me what the d lambda is, right. So, lambda for that reaction, so that reaction has progressed forward by an amount of d lambda, okay. So, this is what is called the progress variable, right, and progress variable is a property of the entire reaction. It is not the property of A1 or A2 or A3 or A4, it tells the progress of the entire reaction. Okay. All right. Now, let us go back to this reaction and let us ask the question, what is the dg of this reaction? And you know where I am getting at. If dg is greater than 0, the reaction is not spontaneous, right, and if dg not spontaneous, and if dg is less than 0, so thermodynamically my reaction wants to go in that direction, right. So, this will be a spontaneous reaction. Right. So, it will just spontaneously react, so that thermodynamically I want to make dg as close as possible to 0, right. So, I have some driving force for the reaction to happen. Okay. Now, so what is then dg? dg is nothing but sigma mu I dni, right. So, this is again mu I dni is from products minus reactants, that is how I am writing it, right. So, mu p dnp minus mu r dnr, that is how it should be looked at as. Okay. So, dg is mu I dni, and instead of dni I am going to substitute the progress variable mu I nu I, that is my reaction, times d lambda, okay. And then so I am going to assume that d lambda is greater than 0, okay. So, I want the reaction to progress forward, but so then I am saying that if dg is less than 0, the reaction goes forward, okay. So, the reaction is what again? nu1 a1 plus nu2 a2 gives rise to nu3 a3 plus nu4 a4, and delta g of this reaction is less than 0. So, which means the reaction should go forward, right. So, that is the direction of spontaneity from thermodynamics, second law of thermodynamics. Okay. And if dg is greater than 0, that is mu again. So, this comes when mu I nu I is less than 0, right. So, because d lambda is greater than 0. So, where the other case, this is case 1, mu I nu I sigma of that, right, and that is if that is greater than 0, right, then the reaction cannot go forward, or in other words dg of backward reaction, which is equal to minus dg, this is for the forward reaction, that is negative. So, reaction goes backward. Or in other words, backward reaction is the spontaneous reaction. Okay. Bear with me, because once we do case studies all these things become more and more clear. So, right now I am just developing a framework to go towards these case studies. Okay. Alright. So, dg less than 0, again it is the same as delta G less than 0. I have a driving force for the reaction to happen, reaction happens, dg, and that is mu I is less than 0, sigma of that. Okay. So, this is condition 1. Condition 2 is the opposite condition, dg greater than 0, sigma mu I is greater than 0, reaction does not happen, or does not happen in forward direction, rather d lambda greater than 0 cannot happen. So, d lambda will be less than 0 and I have a backward reaction. Okay. Alright. So, and at equilibrium dg equal to 0, and so we want to see what happens at equilibrium. Okay. Alright. So, at equilibrium, because thermodynamics is all about seeing what happens at equilibrium, right. So, not when I am away from equilibrium, these are away from equilibrium. Okay. And at equilibrium where dg equal to 0, what I have is sigma mu I equal to 0. Okay. Now, what is mu I? Mu I itself, let me change the color so that mu I of the pure compound, right, at that temperature and pressure, plus kT ln AI, activity, right. So, this equation we know from our solution thermodynamics. So, mu I that goes into this equation for any reactant or any product is mu I tilde, that where that product is a pure product or that reactant is a pure reactant, right. So, it has not gotten contaminated solid solution with something else, plus kT ln AI. AI is the activity when so when I am solid solutioning it with something else. Okay. So, this is how I can write mu I as, and then once I do that, the sigma mu I now becomes sigma nu I, sigma meaning about all products and reactants, right. So, I can have I equal to 1 to how many ever products plus reactants are there, right. So, this is mu I tilde, which is the pure mu I Tp plus kBT ln AI, right. So, and that is equal to 0 at equilibrium. Again we are at equilibrium. Okay. Or in other words, I am going to say that minus kBT nu I ln AI, right. So, I can rewrite it like this, is equal to sigma nu I mu I tilde. Okay. So, now I have come down to pure compounds, right, and this is something that so this is just the delta G of the reaction when it is performed just using pure compounds, right. So, I am just going to write this as delta G tilde of the reaction or delta G naught, that is what you will see people writing, right. So, this is only so if I have magnesium plus half oxygen giving rise to magnesium oxide, so I am going to assume that magnesium at a given temperature and pressure, magnesium oxide is pure, which means magnesium oxide is not in a solid solution with calcium oxide or some other oxide, right, or something else. Okay. Then magnesium is also pure, right. So which means that I am going to so I am at that T and P where magnesium is also pure, magnesium is not contaminated, and so is gas phase oxygen, oxygen is also pure, right. Then the delta G of this reaction, right. So, that is what I am going to call it as delta G naught. Okay. So, now delta G reaction or delta G naught is mu I tilde Tp. This is just for reactants and products are all pure. Okay. All right. So, sorry. Okay. So, now what we have is minus kBT sigma nu I ln AI is equal to so I am going to just call this as delta G naught at a given temperature, right, or I am just going to call it G naught at a given temperature, and G naught we know is delta G of the reaction, and that is equal to sigma mu I tilde Tp. Okay. Now, so let us massage this a bit more. kBT ln pi AI power nu I, pi meaning a multiplication, AI power. So, if I have 2 A1 plus 3 A2 gives rise to some 4 A3 plus 5 A4, right. So, this thing pi of AI is nothing but AI nu I, right. So, is the activity of A1 sorry of A3 power 4 times activity of A4 power 5 divided by activity of A1 square divided by activity of A2 cube, right. If these are all ideal solutions, I can write activities as just compositions, right. So, x power 4 x A3 power 4 x A4 power 5 x A1 square x A2 square. You may have seen this somewhere, right. So, this sort of taking powers of these pre indices, right. So, you may have seen it in some kind of physical chemistry earlier, and so this is where it comes from. So, this is the derivation of it, right. So, and we are saying this number kBT ln pi AI times power nu I, that is equal to minus delta G of the reaction at temperature T, or that is equal to G naught. I am just going to call it G naught or minus G naught, sorry. Okay. All right. So, now I am going to call this number pi of activity, right. So, the product of all the activities powered with corresponding pre exponents, right. So, these numbers, right. So, where the number of reactant molecules and the giving rise to the number of product molecules, that pre index, right, that is my nu I, that I am going to call it Q, and Q is what is called the reaction coefficient. Okay. All right, that is Q, very good. So, for a reaction 3A1 plus 2A2 gives rise to 4A3 plus 6A4, we just wrote it, right. So, Q is now A3 power 4, A meaning the activity of 3, right, times A4 A3 A4 power 6 divided by A1 power 3 A2 power 2, right. So, this we have just seen, right. So, I am just repeating it. Okay. Then kT ln Q is equal to minus delta G reaction of the pure compound Tp, that is equal to minus G naught. Okay. So, I am just going to define, I have defined this quantity to be minus G naught, and so as a result what I have is I am going to define, yeah. So, Q then, right. So, this is at equilibrium. At equilibrium Q turns out to be exponential then minus G naught by KT. Okay. So if I know the G naught of pure reaction, so pure reactants and products reacting to give that at a given temperature and pressure, right. So Q at equilibrium is exponential of minus G naught by kT, okay, and Q at equilibrium, this is a constant, this is some value determined by the G naught of the reaction, of pure reaction, of reaction happening across pure compounds, right. That is a constant, or that is something independent of concentrations, right. So this is independent of concentration, right. So this will be some standard number. Then I have T, temperature is also independent of composition. Right. So this number, right, so where Q at equilibrium, right, so exponential of minus G naught by kBT, this is what I am going to call it K, right, so which is a function of T, and K is what is called the equilibrium constant, right. So now be careful, we have equilibrium constant, right, K is this quantity exponential minus G naught by kBT, okay, and K just defines for me where equilibrium can exist, right, whereas Q, the way we defined it, right, so Q can be defined even away from equilibrium, so Q can exist even away from equilibrium, right. So it is not necessary, although I have derived this at equilibrium, right. So Q, the way I defined pi of all these A3 power 4, A4 power 6 divided by all these things, this can exist far away from equilibrium, no problem, okay. Now the condition then is at equilibrium Q, which knows the material signs, right. So Q knows the material signs of my reaction, equal to K. K does not care about the material signs, K is some constant of the pure reaction, right. So at equilibrium Q equal to K, correct. So Q knows all the material signs. So essentially I am saying how many molecules of reactants combine together to give how many molecules of products. All this information is with Q, right. Q does not know what equilibrium is, but Q knows all the material signs, right. But K defines for me what the equilibrium condition is. When Q equal to K, I have my equilibrium condition, right, and you can actually see that when Q is greater than K, right, and Q has all the compositions, activities and other things, and K is just this number minus G naught by kT, right. At a given temperature G naught is something, some number, at a given temperature kT is some number, so K will be a constant, okay. So if Q is greater than that constant, then the reaction will proceed forward, which means I will be losing more reactants, so that I make this Q equal to K. So if Q is greater than K, the reaction does go forward. I will actually come back in the next class and tell you why. Reaction goes forward, okay. So reaction goes forward means I start losing out more reactants, right. So more reactants start becoming products, correct. So the product concentration is increasing, the reactant concentration is diminishing, right, and to certain extent where then eventually I want to make Q equal to K, okay. So when Q equal to K, then the equilibrium conditions come back again, right. So then the equilibrium is reset. If Q is less than K, then reaction goes backward. Same funda, now I start losing the products back to reactants, right. So it is not a spontaneous reaction anymore, right. So you can actually see this, right. So what is the delta G of my reaction? Delta G of my reaction is yeah. So this is my so G naught, right. So, this is G naught plus this is the Q, right. So, KT ln Q, right. So, I have delta G of the reaction is G naught plus KT ln Q right, and delta G equal to 0 when Q equal to K, right. When Q is greater than K, delta G becomes positive, right. So, that is just simple. So, I am substituting some number that is greater than K, and so reaction, okay. So, I have to okay. So, then reaction should go backward, sorry. So, let me correct this, reaction goes backward and reaction goes forward if Q is less than K, okay. And Q is less than K, then delta G is less than 0, then reaction goes forward, alright. Okay. So, let us stop here for the time being, we will again start from here, there is some confusion at the end, but I will try to again start here in the next class and try to resolve it. But in general, when we are looking at reaction thermodynamics, we are actually going to look at Q's and K's, and Q's and K's are proxy for so what is my delta G, right. So, the Q gives it, and K tells me how far is this delta G away from how far is my reaction away from equilibrium, which wins, is the forward reaction winning or is the backward reaction winning, right. So, let us develop this language in terms of Q's and K's, and so the equilibrium constant and the Q being the reaction so coefficient and equilibrium constants, and then so it's a competition between the reaction coefficients and where they stand with respect to the equilibrium constant, okay. So, let us build it up from the next class onwards, and I will give you some case studies, and all these Q's and K businesses start to ease out a bit, okay. So, if it is intimidating so far, it starts to ease out a bit in the next class, okay. Alright. So, with that let me conclude. Thank you very much.